Good morning. My name is Molly Pembroke, and I want to thank you all for joining us today for our webinar. Today's webinar will focus on optimizing Questa performance. Before we jump in, I'd like to give you a brief introduction to TriLogic and what we do. For over 30 years, TriLogic has provided software and services enabling engineering groups to design, develop, and deliver products through excellent support, training, and consulting services to help you achieve success sooner. Oasis Sales has been a Mentor Premier Partner for over 16 years. Their industry knowledge and experience make them uniquely qualified to understand your business and how technology will make their customers successful. As you can see highlighted on the map are the regions that Oasis and TriLogic cover. Here you can see the different design and product management areas that TriLogic covers. You'll notice we've tried to create a suite of products that will provide a front-to-back solutions all the way from concept to end of life. And now I would like to introduce today's presenter, Walter Goody. Walter has over 25 years of experience in ASICs and FPGA design and holds an MS in electrical engineering from Washington University in St. Louis. He worked for 6 years doing ASIC design at Tel Labs operations. From there, he went to work for Mentor Consulting, where he consulted on various ASIC projects, including time spent in München, Germany, and Helsinki, Finland. For the last decade, Walter has worked as an application engineer supporting Mentor's line of functional verification projects. Everyone, please welcome Walter.
All right, so as Molly said, today's presentation is on performance, verification performance. We'll cover a few different topics here. First, we'll talk about what does performance mean and why people are always interested in it. Then we'll talk a little bit about how to tune the performance of Questa for various purposes, for regression runs, for debug runs, etc., and how you go about doing that. And then the last section we'll talk about is optimizing your debug, so getting performance out of your debug. So if you would talk to me in around 1999, everyone was talking about the fact that there was this upcoming problem with a design gap. And that means, if you look at this curve, this was how big the ASICs and FPGAs are, how big a device the FPGA designers can manufacture, the vendors or ASICs. And then we were looking at the productivity curve of designers, and there was this thought that there was going to be an upcoming design productivity gap. Well, it turns out that engineers are quite clever, and we can just say things like, hey, you know, we've got a bigger device. Let's just take these two independent FPGAs and let's combine them into one. We can, you know, put 4 channels of our filter on there instead of 2. You know, so design productivity didn't turn out to be a big deal because we started reusing logic a lot more. We started purchasing IP either directly or getting it from the FPGA vendor. And so the amount of new logic being designed went down. What really turned out to be the issue was that we couldn't verify all the logic we were putting on there. And so that's why you've seen over the last decade, and this slide getting a little old. It used to be you'd have 2 designers for every verification engineer. Now we've almost flipped that around to the other way, where there's more verification engineers on any one project than there are design engineers. And then if you look at this slide, it's showing that, you know, the majority of any time spent on a project is being spent on the verification effort versus the design effort. And, you know, if you followed that trend to, you know, its logical conclusion, obviously this is a little bit of a joke, but, you know, within about 25 years, all of the time is going to be spent on verification and none of the time on design. So anyway, that's kind of just the background here. So then let's can you make sure that ModelSim and Questa, well, Questa, are running as efficiently as possible? So the first few slides I'll go through are just, a couple of things that, you might consider. If you're doing VHDL designs, make sure, and you're doing mathematic operations in a VHDL design, make sure that you're using the IEEE version of the math packages and not the kind of synopsis originally created, the IEEE math packages. And those are not as optimized as the official IEEE version of those. So that's what gets shipped with Questa. Just keep that in mind. The ModelSim INI is the file that does a lot, it's what configures the simulator, and you want to make sure that you're using an INI file that is from the latest version of Questa. So if you're using Questa 10.7, you really probably want to make sure you're using the ModelSim INI from a Questa 10.7. If you're not, there may be things in there that will affect your performance. Mostly what users use this INI file for is the library mappings. And so what I tell most people is the local INI in your project directory, you can take out everything in there other than the library mappings, and then anything else that you might want to update. So what happens when you first create a project, it makes a copy of the ModelSim INI that's in your install directory, and it copies it to your local project directory. That's okay, but as if that project moves forward and you're copying that directory and you've upgraded ModelSim, you might have an older one. There is a comment at the top of that file that says what version that was from. So, spent a lot of time on that. Here's something that I'm not even sure that I give this recommendation anymore. In the past, the 64-bit version of Questa was significantly slower than the 32-bit version. The reason being it's all pointer-based, and so it's more expensive in both performance and in memory footprint size to carry around 64-bit pointers versus 32-bit pointers. We've really closed the gap to it's 1 or 2%. And honestly, I think in the next couple of years, we're probably going to do away with the 32-bit versions. Avoid using a tickle-based test bench. Hopefully none of you are doing that. That's saying don't have a test bench that's a bunch of force commands in a tickle file. Have it be a VHDL or a Verilog test bench that is you're writing in the language. A tickle-based test bench is going to be really slow. On the other end of the spectrum, if you're doing C programs, so you're hooking up C or something to your simulation test bench via the PLI or the FLI, there's built-in options that make sure that you can optimize. And if anybody is doing that, contact me and we can see if there's a better way for you to be doing that. Signal Spy is something that prior to VHDL 2008, VHDL did not have hierarchical referencing, so you use Signal Spy as a way to do that function. We had basically added hierarchical referencing through something called Signal Spy. Now that there's a native VHDL way to do it, if you're in a VHDL world and you want to do hierarchical referencing, use the actual VHDL style. Again, you want to run at the coarsest time resolution that you can. If you're running your clock rate at, say, 5 megahertz, you could probably get away with nanosecond time resolution. You won't get 1,000 times faster by using nanoseconds versus picoseconds, but again, the simulator is all scheduling based, and it's probably slightly less expensive to say wait 10 nanoseconds than wait 10,000 picoseconds. So you will see some impact by using that coarsest resolution. On the other end of the spectrum, if you go too high on your resolution, then you will probably start to see that your test bench is not operating correctly. So for instance, I know for sure the Xilinx DCMs, they require at least 10 picosecond resolution. So if you're using a Xilinx DCM in your test bench, then or in your design that's generating some clocks, then you have to go at least down to 10 picoseconds. So set it at the lowest you possibly can. Here, if you are a VHDL house and you, for whatever reason, need to do gate level timing simulations, I would highly suggest you use the Verilog gate level models. If you have a mixed language simulator, Verilog will simulate 3 or 4 times faster than VHDL vital models. So VHDL gate level models, the designers of that spec did not take performance into account, and VHDL vital gate level simulations are slow. That is true across Mentor, Synopsys, Cadence, whoever. So if possible, you can still use your VHDL test bench, but generate a gate level Verilog model and just run mixed language with your VHDL test bench and your Verilog gate. Run in batch mode for fastest simulation. So if you're doing a regression test, don't bring up the GUI. How much effect this really has is somewhat debatable, but there is some overhead to bringing up the GUI. Generally, that should be pushed off to another processor core, but it may have some effect of just updating the GUI, and you may slow down the simulation engine a little bit by running in GUI mode. So here, I always say, it doesn't matter if you keep your source code on a network drive. It doesn't matter if you keep your compiled libraries on a network drive. But I would say try to make sure you keep your WLF file and potentially your log file on a local hard drive. You don't want network latency slowing down your simulation. So keep those 2 files local, if at all possible, and consider an SSD for your local drive, because that is often one of the things that slows things down the most, is the writing of this WLF file. Questa Sim is the simulation engine that's going to run all of your simulations. Questa has a few steps that happen to get you up and running. So you have your design files, you run them through your vlog and your vcom to compile them. There is an optimization step called vopt, which basically looks at all that code, and it does a simulator optimization. And so it does all kinds of software optimization things like inlining function calls, merging parallel always blocks that have the same sensitivity list, all kinds of maybe getting rid of signal aliases. So if you have 15 different names for signal, it might want to collapse that down to one signal that it has to keep track of rather than 15 different things. And so all of these things together, it creates a more optimal simulation database. And then once you've done that optimize, you elaborate. That is getting the simulation up and ready to run, and then actually running the simulation. So this step right here, this optimization, can really affect how long it takes to run a simulation. Shown again here, it is that there's really 3 steps that's happening. There's the compile, there's the optimize, and then when you say vsim and invoke a simulation, you elaborate it, and then when you see run, you start running the simulation. So basically, it is this optimization step that we're going to talk about, how to configure that optimization to make your simulation run the fastest. Now, some of you may not even know that that optimization goes on, and you may be doing this two-step flow where you just do your compiles and then you say vsim and you start to simulate and don't even realize that that vopt step is going on. And so that is, if you do the two-step flow, if you just compile your code and then you say, let's launch a simulation, what happens is this vopt happens at the beginning of that simulation step. And you'll see this little line of code. The first line in your transcript will be design is being optimized. If you're not seeing that, then that means you may have vopt turned off, which will slow your simulation even more. Now, a lot of people like this because they came from the model sim world. They don't necessarily want to do that three-step. It's easy to do this. It implicitly does the vopt, but the con is when you launch your simulation, it will do that vopt every time. And you may not want to do that vopt at the beginning of each simulation step. So it takes a little longer for you to invoke your simulation. And the other thing is you don't want to do this for regression runs, because if you're running a regression suite, you probably only want to optimize your design once, because you're running the regression suite a whole bunch of different tests on the same DUT that is not changing. So let's do the optimization once and then run a bunch of simulations. So the three-step flow is that you do your vlog, vcoms, then you actually explicitly do a vopt, and then you do the vsim to run your simulations. So the pros of this is that it is much more modular. You have a lot more fine-grained control over this vopt. You can pass arguments to vopt in this flow, but it's a little more difficult. And then you have a lot more flexibility over here. So let's look at some of the considerations here. If you're doing a simulation and you want to debug that simulation, so if you're not doing a regression run and you're wanting to, figure out what's going on in this design, you're going to want to put signals in the wave window. So if you say vopt and just let it completely optimize the design, what will happen is it may optimize away certain signal names because they are redundant, because the way the optimization was done, it just didn't need that signal in there. So now you go to put that signal in the wave window and it's not there. It says, I don't know what signal A is. Well, that's because it was optimized away. So the way that you can preserve visibility is through this switch to the vopt called +ACC. And so here's a spot where I'm saying, okay, let's compile my test bench, let's compile my DUT, let's launch a sim on my test bench, and then I'm passing to the vopt through this -vopt args, I'm passing +ACC, and I'm preserving all of the DUT signals. The constraints that you can put on ACC, you see, are if you just say +ACC, it's going to preserve all the visibility in both the test bench and the DUT. By doing this, +ACC +DUT, I've only preserved the signals in the DUT. But I might want even more than that. Preserving that visibility probably, it does cut down the amount of optimization that happens. So, it'll make things run a little slower by saying +ACC. So if I say +ACC just the DUT, well, now I'm still allowing it to optimize the test bench. But I might want to say, I can go a little deeper. I'm currently debugging the transmitter section of my design, and that's maybe 20%, and all this other part of it, I can let that be fully optimized. So you might even go deeper and say, +ACC +DUT transmit or something. I'll show you some of the arguments here. So +ACC preserves visibility. You can say only preserve signals, nets, ports. You can preserve parameters, you can preserve all these different pieces. And let me just show you a few different things that you might want to do. So right here, plus ACC, vopt plus ACC, and then I would give, all my arguments and output a optimized database. So plus ACC, I don't agree with this. I think it's not so much disable all the optimizations, but preserve all visibility, which does limit the optimizations. So here I've stepped back and I said, you know what? I don't care about parameters. Well, I have nets, ports, and registers. So I don't care about parameters. I don't care about local variables. I don't care about a whole lot of other stuff. So I'm just going to preserve those three pieces. Right here, I've said vopt plus ACC, and then I've said, let's preserve all the things in the instance name top. So I've preserved all of the objects just in the instance name top. Now, if I need to go deeper into my design, I won't have those other things. So if I need to go a little deeper, here what I've done is I've said vopt plus ACC, and then I've said the instance name HFTX, and then this dot says preserve all of its children too. So if I had to put a dot here, that would have preserved everything from top on down. This says, as I'm optimizing this design, every time I see an instance name of HFTX, preserve that and all of its children. And another way to do it is you can give a hierarchical path. So right here, I'm saying preserve the registers and the nets of top /U1. So the U1 instance below top. And then here, did a similar thing. I'm preserving the registers and nets of top /U2 and 3 levels down. So I can say something like go down a few more levels from there. So if you have top level parameters in your design, you have to treat that somewhat carefully. So for instance, in this design, I've got on this module right here, I've got a parameter called size. And if I say vopt and I fully optimize top and I output it as top_opt, and then I say I want to simulate on top opt, and I try to set that parameter, I get this command saying there is no parameter called size on this guy, and that's because I didn't tell it to preserve that when I did this optimization. So you have two choices there. You can either override the parameters when you create the optimization. So right here, I said, I created vopt on top, I output top opt, but then I set that parameter right here in the optimization, not in the simulation. And I might have said I want to call this top opt 4, because I set size 4 here. And then I say simulate and it goes. That's good if I'm testing a couple of different values. So if I want to test size 4, 6, and 8, I might create a top opt 4, a top opt 6, and a top opt 8. But if I want to test size and I want to test it from size 0 through size, 1023, I probably don't want to create 1,000 different optimizations. So in that case, I don't think I have this on this slide, but I can say float param size, and then that will preserve that parameter. So at simulation time, I can go ahead and run that at 0, 1, 2, 3, 4, 5, up to 1,000. You'll get a slightly less optimal optimization, so slightly less speed, but you don't need to create 1,000 different optimized net lists in that case. So any optimized net list that you create, that actually gets stored in your work library. So for instance, here, I've got a design and I'm going to say, okay, I need to do full debug on this. This is the version I want to use for debug. So I say vopt plus ACC on top, and I output something called debugger. So now that exists in the library. And then I say, okay, for regression testing, I want to run as fast as possible. So I'm going to do no plus ACC. And then here's a couple of things that if you're doing gate level, you can turn these things off and it'll speed things up. And I output that as opt-ver, as optimized version. And then maybe I'm going to do code coverage. So I say vopt and I do my coverage options and I output that as the cover version. And then maybe I've got some parameters in there. So I set those parameters different size. So now all of these different things, I can now say vsim debugger. And I can, say, first maybe I'd say I'm going to run vsim optver. And I run it for a while and it says there's an error. So I say, okay, I got to debug that. So now let's do vsim on the debugger. I don't need to recompile because that exists in the work directory. So I can just say vsim debugger. And then I say, okay, now that's all good. I've done my regression suite. It says everything's good. Let's go ahead and run a code coverage on the code coverage ver and collect some code coverage. When you're running vopt, it actually locks the library while it's doing that vopt. And so that's just something to keep in mind. If you have a lot of really short simulations that the vopt might take a minute and then the simulation takes a minute, the problem there is that vopt, if you're kicking off a whole bunch of simulations, the vopt will lock the work directory. Some other simulation might try to kick off. The work directory is locked, so it can't get in there. It's got to wait till that lock is released, and then it can do its thing. And so if you are doing that kind of a simulation, it's probably best to do that two-step flow and pre-create it, or every one of those simulations might want to have its own local work directory that it can work on. Batch level simulation, I'm not going to go too deep into this, but we used to use the argument -c, which was command line. We now suggest you use this argument -batch because it allows you to not use standard output as your log writing facility. Standard output is kind of expensive. It's kind of inefficient. And if you use the local built-in file creator, it'll be better. And so, for high performance, use -batch and, no standard out. So regression suite. There is within Questa something called checkpoint and restore. And what checkpoint does is it says, let's create a map of the state of my design. And so you can run your design for a while, create a checkpoint, and then terminate the simulation. And then you can start the simulation and say, restore that checkpoint. So checkpoint and restore, the easiest use of it is for disaster recovery. If you've got a simulation that runs 5 days, you probably want to checkpoint it every 4 hours or so and create a checkpoint. And what that does for you is if 3 days into your 5-day simulation, you have a thunderstorm and the power goes out, you can restore the last checkpoint, restart your simulation from that point, and only need to simulate for 2 more days. So that's the easy way to use this. The other way to use checkpoint and restore is if you have a simulation that, maybe it has a training phase. If you have a PCIe bus, the first thing that happens is you come out of reset and the PCIe bus goes into this training phase. And that training phase is negotiating speed. It is, enumerating the buses, doing all this stuff. And that might take an hour of simulation time just to get the PCIe bus trained up. And then after the bus is trained up, you go off and you start running some simulations. And if that that stuff that happens after that training phase only takes 20 minutes to simulate. Well, now it's an hour and 20 minutes to train up the bus and run a simulation. And then you want to run a different simulation. You start up, you have to train up the bus and then run some other simulation. Well, what if you thought about that, you could create a checkpoint after the training phase and then restore that checkpoint and run a test, and then restore that checkpoint and run this other test. So now instead of each simulation taking an hour and 20 minutes, the first one takes an hour and 20 minutes, the next one you restore and it only takes 20 minutes. But the catch is that you can't change any code between the checkpoint and restore. So if you change one line of code, now the restore state does not match the state space of your design. So what you need to do is be creative and say, okay, I got to tell the simulator what test to run. And maybe you do that through a force command, or you read a file, or you do something. But if you have a simulation where you have this long training phase, this can be really helpful. Another thing to think about when you are doing a whole set of tests is this idea of creating a pre-optimized design unit. So in this case, I'm saying I have a DUT, and in this case, maybe it's a gate level netlist or something, but it could be anything. So here you'll see I've compiled my ASIC library or into the work library ASIC lib. I've compiled my cell library, and now I've compiled my design under test. So those are both compiled. And then I'm going to do this command right here. I'm going to say vopt. I'm going to bring in that ASIC library, and I'm going to bring in my DUT, and I'm going to output something called .opt. But I'm flagging that as a pre-optimized design unit. And so what that does is, this is the big thing. This is what takes a long time to do that optimization. And rather than do that every simulation, I'm going to do it once and create this pre-optimized design unit called .opt. And then I'm going to go ahead and compile my test bench, compile a test, and I'm going to launch my simulation. And my simulation is going to go, okay, I see I've got this thing called test bench, and I'm going to optimize that because I'm not doing a vopt on this test bench, but it's going to say, okay, I got to compile the test bench, but I see that the test bench instantiates something called DUT. And I also see that I have this thing called .opt, which is a pre-optimized version of that DUT. So what it does is it pulls in the test bench to test, optimize those two things, pulls in the pre-optimized DUT, and runs a simulation. So for this first one, that didn't really save me any time. But then my next test is that I've got the same test bench. I'm just compiling a different test, and I want to run a simulation. So all I have to do is compile test 2, launch that simulation, and again, it says, okay, I'm going to optimize the test and the test bench, but I already have a pre-optimized DUT, so let's run that. And then let's run another one, and another one, and another one. And what that ends up happening is, instead of you having to do the whole vopt and then run your simulation each time, you do the optimization once, and then the other pieces in theory are shorter. So this is good if the optimization time is significant compared to the amount of time it takes to run a test. So here's another thing that I've seen people do, and it's kind of interesting, and that is, okay, I've got this design under test here, and you know, it's a big design, and I'm running my simulation, and I find out I've got a bug in this block right here in block C. So block C is 10% of my logic. So I run my simulation with my whole test bench and my whole design and everything else, but then while I'm running that simulation, I'm going to dump all the I/O that was going into and out of block C, and I'm going to dump that into something called a VCD file, a variable change dump file. So I'm going to run my whole simulation, save that VCD file, and then I'm going to go and I'm going to take block C and I'm going to start to make some changes to see if that fixes the bug that I found. And instead of running my whole design, because I don't have a test bench for block C, I can say vsim just block C, and I can use as stimulus that variable change dump file that I saved earlier. And so now this is only a small little design. It's going to run real fast. I can make some changes, run a sim. It can apply the stimulus that was saved in here. I can debug. I can do that several times. Finally get back to, okay, I think I've fixed the problem. And then I'll go back and I'll run a top level simulation with C plugged back in. So it's just an idea. I almost don't talk about this anymore because it is the default. But in the if you're running Questa on Linux, it will automatically take the waveform writer and it'll put it on a different thread, which means on a multi-processor system, the waveform writing is not going to be, you know, wrapped up with the simulation engine. It can run on a different CPU core and it can speed things up. On Windows, unfortunately, due to the nature of Windows, it is much harder to break that thread out of the main thread. And that comes back to the, you know, that kind of brings up the question of, is Questa multi-threaded? Is it helpful to have multiple CPU cores? And by default, Questa is not multi-threaded. It is, the simulation kernel is a single thread. The GUI, the wave window, on Linux, the WLF writing, those are separate threads, but the simulation kernel itself is a single thread. So having a multiple CPU core machine is not necessarily helpful because usually what you'll see one CPU core maxed out at 100% and then one other one that is doing all the other background tasks, and it's maybe at 5-10%, and then any other CPU core is just going to be idle. Now, I don't really talk about it in this presentation, but there is something called Questa Multicore, which allows you to run your simulation, do some profiling. Say you want to try to break it up to multiple CPU cores. This partitioner figures out, you know, it tries to find partitions with similar computation loads and as little communication between those as possible. The reason I really don't talk about that too much, though, is that it's expensive. It's one license per CPU core, and you get about a 50% efficiency. So, in other words, if you use 4 simulation cores, it will run about twice as fast. If you use 8, it'll run about 4 times as fast. So if you have a regression suite, you're better off running single tests in parallel. The only time multi-core is really useful is if you have one honkin' simulation that takes a week to run and you want to try to bring that down to a day or something. You might use a lot of simulation licenses to do that. Next begs the question, how do I know I'm getting the fastest simulation I can? Where is all of my simulation time going? And that is where we have something that allows you to do a profile of your design. So the first thing you need to do is do some baselining. You need to figure out, where am I, and, you know, how can I improve? So there is a command that we have called SimStats. So if at the end of your simulation, before you terminate, you say SimStats, it'll print out this little thing. Or you can give an argument to vsim. You can say vsim-print SimStats. And then before the simulation terminates, it'll print out this. So what SimStats does is it gives you a couple of things. It says how much time was spent in the, if you've done the two-step flow, it'll say how much time was spent in vopt, how much time was spent in elaboration, and then how much time was spent simulating. And it'll give you two different things, and it's mainly the simulation one I'm looking at. It'll give you clock time, how much wall clock time was spent and how much CPU time. CPU time is usually the one that I would look at, but you want to make sure those are at least somewhat similar. Now, one thing that can happen if you're writing a lot of waveforms is you can actually see that CPU time is actually bigger than wall clock time. And that will happen when you're writing a bunch of waveforms and those are pushed off to another processor core. So CPU time is the sum of both of those, but some of that stuff is happening simultaneously. CPU time can be bigger than wall clock time. Don't get freaked out if you see that. So once you have that baseline that you're saying it takes 2,500 seconds to run my simulation, now we can use the profiler to look at, how much time can we save? And what the profiler does is it helps us to find inefficiencies in your code, and it also helps Mentor find inefficiencies in our tools. So what the profiler does is it samples the source code as you're simulating, and every once in a while it will say, what line of code am I executing right? And it'll record it. And so maybe every 60 samples per second, I guess, is the default. It'll just pause and it'll say what line of code is currently being executed. And if you run for enough time and you collect enough samples, what that then gives you is basically a view of how much time is being spent running any one piece of code. If you collect enough data, you'll get a statistical graph of, where am I spending time. So to turn on the profiler, at the beginning of your simulation, you can say profile on. Then you run, you can save the profile database, and then you can debug the profile database. So basically, I would turn on the profiler, I would run my simulation. At the end of the simulation, I'll save the profile database, and then I can bring that back up and I can look at it. So there's a few different views that you can get. There's the hierarchical view, which kind of shows you from the top down, how much time. So in this case, you can see this assertion right here. It's an assertion on line 121 of some file. 74% of my simulation cycles are spent, executing that assertion. And 18% of my simulation cycles are spent executing this one. That's the kind of thing that you don't want to see, because that says I probably messed up my sensitivity list and this assertion is just operating all the time, and I probably spawned thousands of copies of it that are all doing things. And if I clean that up so that 1 or 2% of my time is being spent there, then everything else is going to run much faster. And so there's a bunch of different views. You can look at the ranked view. You can look at probably that call tree is the one that I use the most. You collect that information. You try to find those inefficiencies. You clean up those inefficiencies, and you'll see your code will run much faster. So in this particular case, like I said, that assertion had an incorrect sensitivity list, so it was triggering constantly. And so the simulation was constantly in there. Once we fixed that and dropped that down to 1% and fixed that other one, the simulation ran about 100 times faster because all the time wasn't being spent in that one thing. So that's simulation performance in general. So now let's talk about, okay, we've been talking about how to make the simulator run faster, but let's talk about how to debug a little more optimally. This was another one of these Wilson's group studies. You'll see these in the IEEE all the time. We asked a bunch of verification engineers, where do you spend your time? And they said about a quarter of the time is spent running simulations. About a quarter of the time is spent actually developing the tests. And about a third of the time is spent debugging. So everybody always says, I want my simulator to run faster. So let's say we, magically made a simulator that ran twice as fast. So we would save about 13% on our simulation time. So that's nice, but simulators running twice as fast, we only gain 13%. If we could develop tests faster, we would gain, 14%. And then right here, debugging, if we could make the debugging more efficient, that's where we actually save the most amount of time. Looks like we asked the same question again, and we were a little more specific, and we said, how much time is spent in planning, how much time is spent in developing the test bench, in running the simulations, and then debugging has gotten even bigger in 4 years. And I think we have a new version of this that shows debugging is up to about 50%. So debugging, if we can speed up debugging, that's actually the biggest savings we can get. If we look at this, debug is our biggest chunk. So yes, making a faster simulation will mean you're waiting less time at the coffee machine for the simulation to run. But once you get into the debug, if we could make that more efficient, that's an even bigger benefit. So instead of kind of paraphrasing Henry Ford, if I asked people once they wanted that, I said faster horses. We want the simulator to run faster. What instead Henry Ford did is he changed the game. He said, let's not make horses, let's do something different. And the something different is, let's have a better way of debugging. And that is where the Visualizer debug environment comes in. So Visualizer is a separate product from Questa. So it is an add-on. Questa has the traditional Tickle debugger. It is a decent debugger. I'm not saying that it is bad, but it has a few flaws. The flaws are that designs have gotten so big that database structure, that WLF file, has reached its limits to some extent. Visualizer can have much higher performance on a much bigger data set. So now that, you're doing, the ultra scale parts and collecting tons of data, we've seen the traditional debugger start to bog down. Visualizer is able to handle that. It is more intuitive and easy to use once you get used to it. You've got a lot less clicks to get to the same data. And then if you are doing system Verilog UVM test bench, then it has a much better UVM aware debugger. UVM is the one place where you will have to use Questa Prime. The debugger is the GUI model is much faster. We can handle much larger designs. The debug is more efficient, and I think I'll just get in to show you some of the things there. There are schematic views built in, so it's all very integrated with each other. It's much more efficient. And then here is what I'd say is almost the most compelling reason to use Visualizer. And that is the way the waveform data is recorded is much more efficient in simulation. So if you're doing a regression run, you're not collecting any wave data. Let's say you had a simulation that took 10 minutes to run. Now you say, I need to debug this design. So I need to put on that plus ACC switch so that I can collect all of that data. Just turning on that plus ACC switch slows your design down by about 2x. So now just turning on that debug, the inefficiencies of the optimization, because I have to preserve all that data, means that's going to run 20 minutes. The same switch, you don't use plus ACC if you're using Visualizer. You say -debug, and that has almost no effect on how much time it takes. Now you say, let's collect all of the signals in the design. Let's do a log-r star and collect all the wave data. Compared to that debug or that regression run, collecting all of that, you're going to have about a 7x impact on simulation time. With Visualizer, collecting that same data, you're only about 2x slower. So your debug simulation runs are going to be much faster for Visualizer because it has a much more efficient way of collecting that data. And then here's some design examples. I'm not going to go deep into those. The question someone had was, if you have a breakpoint in Questa and you want to, is it possible to go backwards to see the functions where that came from? And in the traditional debugger from that we have, the answer to that would be no. With Visualizer, the answer is yes. So that's another benefit of Visualizer. And the way that happens is you can turn on the execution flow. And I think I'll show that in a slide or two. The source code window is fully integrated with the simulator. So anytime you click on anything in the sim tab, it'll show that source code, it'll show that schematic. So all the windows are completely connected. You can do these traces both backwards and forwards in Visualizer. You can get to any time. There's something called this time cone view, which I think is unique to our simulator. And that is, you know, if I go into this time cone view and I put a cursor somewhere and I say, okay, I want to look at this point, and I see that this signal right here is going from 0 to an X at this point, it will trace backwards, you know, and show you the schematic of where that signal came from. But what the time cone view is that it is actually sequential logic aware. And so it says, hey, there was a flip-flop right here. So I'm going to put the cursor here to show this, but then right here, I know what clock did that. So the data I'm going to show here is from the clock before. And then here's another flip-flop. The data here is from the clock before. And then, you know, here's a RAM, and so I can see the data here is from the clock that loaded that RAM. And so that time cone view is sequential logic aware, which is kind of an interesting point there. There's a lot of different search engines. There's an assertion viewer. So one thing that Visualizer currently is only available on the Linux platform. We have, well, we're a little over time, but I want to just at least real quick bring up Visualizer just to show you. I've already run a simulation here, so let me just bring up Visualizer real quick. So real quick, run through Visualizer. So you can see right here I have the source code, and one difference right away is you'll see if I click on any one of these modules, you'll see that source code window automatically updates to whatever I happen to be clicking on, which it's kind of a pain in the Tickle debugger. I think that you end up opening a bunch of different source code. So then there's also a schematic view, and you'll see if I click on an instance, it shows its schematic. If I click on this instance, it shows its schematic. Then if I zoom in, you'll see here's this red block. If I click on that, that is an instance of another design. So that's an instantiation. These blue blocks, those are sequential processes. So it's a process with a clock. These open blocks are combinatorial processes. So you can see that all of this is completely integrated. When I click on something here, it highlights whatever I click on in the source code window. I can double click on one of these instantiations. It'll push down into that instantiation. I click on this block. Let me turn on, or let me show you, there is a finite state machine. So if I click on a block that contains a finite state machine, it'll show me that finite state machine. If I click on that, it'll take me to that point in the case statement. So I can quickly navigate around. And then, do I have execution trace turned on? I believe I do. So let me add everything from that to the wave window. Let me zoom in a little bit. And so if I put my cursor here, and that is on P and decode. So you'll see now I'm on P instance decode. If I turn on execution trace, this will show me all the code that led to me being into there. So you'll see when I hit this always block, I did that. I came down to here, and then I went into fetch, and then that assigned PNT code. So you'll see it shows you the trace of all the code that got you to where you currently are. And if I click on any block, it'll show me what code was active during that particular, at that instant in time. So that instance trace is really nice. And I think, unfortunately, we're a little bit over time. So I'm going to kind of terminate the demo here. Let me just go back. And Visualizer is high capacity, handles any design size with no lag. It's very integrated. It's got a full UVM debug, much quicker to get to your debug. It is a add-on to Questa, so it's a additional debugger, and it only runs on Linux. So summary for today was we've been making significant investments in speed of the simulator, in efficiency of debugging. We have, a new generation of simulators that are as fast as we can make them, that are as efficient as we can do. That's kind of where I will terminate it there. Are there any more questions before we end the seminar? All right. Thanks, everybody.